He has been an engineer over 20 years, and certainly everybody knows that he is Mr. Skyscraper. And the amazing thing for me is not only that he is really sharing all his knowledge, that he is passionate to tell everybody, and it really doesn't depend if this is a well-known engineer or if it's just a first-year student. And in a personal talk or certainly in a public lecture, he's telling his knowledge, he's sharing his passion on engineering. I find that very fruitful for our discipline. But also he is pushing his environment, not doing things the way it has been done all the time. He is really interested in bringing research into the everyday practical work. That was the famous research or structural research group he had at SOM. So it is about creating new ideas and technologies and pushing the borders every time forward to get to get more efficient structures and in accordance with a meaningful architecture. So in a way, we also can say he's not only Mr. Skyscraper, it's also Mr. Geometry. The lesson is about geometry and the design of tall buildings, and I think geometry is really a passion of him as a key of structural design, structural efficiency, and architecture. Bill, welcome to our last lecture for today.
Thank you very much. I'm very, very glad to be here, and I'm very glad that Mike asked me to be here. And as you mentioned, I'm with Skidmore, Owings & Merrill, which is architects and engineers. And as Philippe says, our initials are SOM. It really means stay on module. Okay, that's kind of essential of our architecture. And I'm going to talk about other geometric concepts which relate to the design of tall buildings. Why does structure matter and why does geometry matter? Well, first of all, structural systems are the essence of the efficiency of a building for sure. And in my opinion, is that geometry is the critical aspect of structural systems. And also, geometry is the intersection of architecture and structure. You know, as you describe, a building. Our goal is if you describe the architecture, you're at the same time describing the engineering, the structure. And if you describe the structure, you can't help but describe the architecture, that they're one and not separable. And I'm going to give a little, some terminology which we have found very helpful in our work at SOM, which is the terms of geometry. We have the design domain, which is where structure might exist. We have a topology, which we call, well, what is connected to what? And then shape is how you take that connectivity and move the nodes around or whatever to get a shape. And finally, you size the elements. So those are the three geometric aspects. Clearly, as I'm going to show you, topology and shape are the most important. Topology and shape is architecture. And that's why we, as engineers, need to be essentially in the creative process in the creation of topology and shape. Now I'm actually going to give you an equation. I'm going to do something, a Maxwell load path theorem to demonstrate why geometry is so incredibly important. It's, this came from Maxwell. And here I have a truss. It has some external loads. It's all in equilibrium. So there's compression forces, there's tensile forces. Well, I'm going to keep the forces and throw the members away, all right? And so now I have a bunch of forces, and they're all in equilibrium, and I'm going to take those forces and I'm going to shrink them to a dot. I put an arbitrary origin there where that arrow is, and I'm going to shrink everything to the bottom, and we're going to discover, as Maxwell pointed out, that if you take the force times the force of all the tension members times their length, minus the force of all the compression members times their length, it's equal to this dot product, which is the external loads and reactions dot product to a point. Generally, that term on the right-hand side is a constant, which means if you have an inefficient structure, you pay for it twice, once in tension and once in compression. And I'm going to give you a little example here. Here I have some loads that are in global equilibrium. I got a point load out there at the tip. There's the reactions. There's 3P coupled in the vertical load at the bottom. And the dot product is PB. And think about it. We do not even have a structure, but we know the difference between the tension load path and the compression load path without even knowing the structure. And so let's throw a structure in there. Here's one. Let's calculate the compression load path, which is 3P times 3B, so it's 9. The tension load path is the square root of 10 P times the square root of 10B, which is 10, and the difference is 1. Exactly what Maxwell told us to be. The total is 19. Well, how much does it deflect? Well, for this particular case, if you go to virtual work, you have 19 sigma B over E. And what's the volume of material? Assuming it's constant stress, you take the load path divided by stress. And it's, for this particular case, all these coefficients are the same. Well, let's try a different answer. Let's try a different solution. Okay, let's go to the Pratt truss. So we've gone from 19 down to 17. Let's go see Mr. Warren. Now we're down to 15. And so what we've done is we've actually have less material and it moves less. We did not make it move less by adding material. We made it less by changing the geometry and actually using less material. And here we have, let's take those two trusses, A and B. Assuming they have the same stresses in both tension and compression, I want you to guess how much more material you need for the one truss A versus truss B. The answer is 27%. And this is the one that really drives me crazy. How much if you have the same deflection? 60% more material. Unbelievable. What's the difference between the two? Geometry. This is why we need to understand the geometry and why I think geometry needs to be central to our designs. As has been pointed out many times, we have a climate crisis today, and day one, most of that embodied carbon is ours. It's coming from the structure. And a logical question is, how low can we go? And so let's use a discrete Mitchell truss here. And remember, we were down at 15, now we're a little bit less than 14. It's a little odd looking. It's got some unusual geometry, which I'll talk to a little bit more here. But it goes down, and this has only 8 members. I've had a lot of members. I go even a little slightly lower, go from 13.9 down to 13.17. And so, a lot of connections. Is this the least expensive? No, it's got a lot of connections, okay? But it does give you a benchmark, so you know how low could I go? And then you can make a meaningful decision about your design. One of the engineers in the office was chewing on my leg about, oh, you got too many compression members and buckling. So I did one with just only one compression member. And this is less efficient, but it's interesting to note that because this is a Mitchell truss, we did not design this, nature designed it, okay? And it turns out, through nature, each of these angles are identical, and it turns the load downward. And so let's talk a little bit about the geometry of Mitchell trusses, and I'm going to show how this relates to tall buildings. Who is Mitchell? He Australian engineer who was educated in Cambridge in England. He wrote this paper on the limits of economy of materials and frame structures, which is essentially trusses. The first word of his paper is Maxwell, okay? And the first equation is that load path theorem I just showed you. It's the tension load path minus the compression load path, he says, equals to a constant, which is true for a certain class of problems. And so here are the geometry of his solutions that are in his paper. And here you have the semi-infinite space, you got this load and these reactions. Here you have this cantilever coming off of a rod and this logarithmic spiral. Here you have infinite space, the load in the middle and 2 reactions. Look at them for a minute. What do you note about the geometry? What does nature want to do? The load in this rim never changes. it just gets redirected. The load in this outside core never changes. It just gets redirected. The load in this outside core is constant all the way down. And the tension and compression members intersect at 90 degrees. And all they're doing is turning the loads. Nature wants to do the load changing gently. And Arik Mazurik in our office guy did this research, and this is the rules of the geometry. If you had an infinite number of members, this would be two 90-degree angles, because you have a finite. All the error is thrown into this angle, and in this geometry, that angle equals that angle equals that angle equals that angles. These offsetting angles are 90 degrees. And if you have a more complex version of the truss, and you look at the way the geometry changes, it changes in a very consistent, gentle way. And if you go even further, it changes the same in both directions. And it turns out, because of the geometry, all of those nodes lie on a circle, which, as you may know, maximizes the area enclosed by our quadrilateral, and it happens to be equal to the Gaussian curvature of the area stress function. So, this incredibly deep geometry that's out there. Okay, Mike told me I had to talk about tall buildings, so here goes. All right, so how does this relate to tall buildings? Well, there's been a lot of work on what you might call bounded Mitchell trusses, what they might look like. But we were doing a lot of topology research in the office, looking at things. I mean, we're the firm that did the John Hancock building in Chicago. You'd think we understood bracing. We didn't. We said, well, somewhere between 45 degrees and 60 degrees, maybe. How many patterns? No, we didn't really know. Anyway, so we started doing this research. We kept on seeing this unusual geometry, we call it this high-waisted X bracing. And so we got curious, and we started, well, let's do some virtual work calculations. And guess what? It does work. That this wants to be at the three-quarter point as it comes around. And then as you take this, and then the question is, how many modules should you have in a tall building? So we were able to derive some things. And you end up with essentially this. And here's my interpretation of what's going on here. The wind comes in sideways, and it has to make 1, 2, 3 turns. Okay, so 90 degrees. So it does a 30-degree turn, another 30 degrees, and then goes vertical, 30 degrees, moving the loads gently. And it turns out that in this structure, that's a 30, 60, 90 triangle. And that's the sweet spot where you actually get the minimum. And depending on the density, you get these other things. We're not quite sure we got the geometry perfectly right at the base, but and all these quads are inscribed in a circle. So that's about the geometry of this efficiency of load path as you take the loads back. I want to talk a little bit about the geometry of symmetry and anti-symmetry and how this relates to design. So here we have a symmetrical structure. These are symmetrical. Here it has symmetrical loads, and here it has anti-symmetrical loads. So and symmetrical loads are like gravity, thermal, creep, shrinkage. Anti-symmetrical loads are like wind or seismic, things that go lateral. And so in this case, the red are the compression, so so that X is in compression. But over here, this X is in tension and compression at the same time. And so clearly, this guy wants to buckle. Okay, it's all being compressed. But this guy is neutral. The tension guys don't want to buckle, the compression guys want to buckle, and they duke it out, and it's a Mexican standoff, okay? Doesn't move, all right? And so if you look at this, what happens is you want to keep the gravity loads in the columns, but they want to bleed into the diagonals, and you don't want them there, okay? And so what can you do? I'm going to show you 2 solutions that we've used in our architecture to address this. First of all, let's talk about the nature of the problem. Let's say this is a conventional structure, and there's a horizontal that's not shown here, which is behind the glass, if you will. And as you put the loads on, and this could be thermal loads or creep and shrinkage and anything gravity, the diagonals are sucking up the load that you don't want them to have. Okay, but when the wind blows, you get tension and compression, And what happens is that you have these, very large loads, a lot of which are loads you don't even want to have. So what if we reduce, do a release, which I'm going to show you here in a minute? There is no load from the gravity. It still resists wind, and your forces are half of what you had before. And this leads to an elegant design. So here's a project we did. This is in North Sydney, Australia. Here's the floor plan. It's got a pretty decent view. You get to see a good bridge out here, from the building. And so what we did is, we had like a party wall on one side, so we put the elevators on one side, and we want to keep this building, so we had basically a concrete building. So we're going to do a steel-braced concrete building, which normally you would never do because of the creep and shrinkage and all those other problems. In fact, we're going to even put it outside the window, all right? And so what we did is we have this joint in the middle. There it is. Of course, it's the high-waisted bracing, okay? And we had this joint in the middle that breathes in and out. So it does not transmit symmetrical loads, but only transmits anti-symmetrical loads. So it's able to resist the wind. And we have this bearing on the inside. Now, and that's, of course, you have to express it with the reveal and stuff like that. You still have to worry about somebody knocking it with a window washing machine. So remember, it's neutrally stable from a buckling point of view. There's as much, all the compressing force is coming from tensile forces. They can't exist separately. Okay, so here's a more recent example. This is from Chicago, okay? 800 West Fulton, a lot of good restaurants, okay? If you come to Chicago, go to the West Loop and hit the restaurants. Here's this building, and it looks a little odd, okay? It's a steel-braced concrete building. And those, I think those diagonals are quite minimal and small in size. And I hope you feel elegant. And here it is, but we used a different solution, okay? Imagine that you had that X bracing and you left it there, and you didn't design it correct. And the loads come in, and it buckles. Okay, good. It just got rid of the load, okay? So what we did is we pre-buckled it, all right? So if you look at the four corners, form a plane, and this node is 600 millimeters outside that plane, all right? And we're talking Chicago, cold winters, hot summers. That bracing moves outward about 125 millimeters in the summertime and pulls in about 125 millimeters in the wintertime when it's cold. And you can see here, we put it out of plane. We did, of course, buckets and buckets of calculations to prove that we were right. But it only it does not pick any thermal loads. It doesn't pick up our creep and shrinkage, which are from our gravity loads. It only moves in and out. And so we had to do this. We thought about door hinges, but we weren't ready to go there yet. So what we did is we used a high-strength, thin steel plate that could flex at very low stresses. Mike was talking about a project where the thinner you make it, the less the stress, right? So what we want to do is we want to make this as thin as we could and still have enough strength to resist the wind loads. And so that's what we did here. Here you see it under construction, okay? And as you look up, we did it on both. It flexes back at the building support, of course, at the middle. Here we have the inspectors on site, Paloma and Mike, just to be, just checking it out to be sure that the detail is good. All right. Now let me talk about the geometry of plan. Now, when you look at it, we still call it the Sears Tower. Okay, it's the Willis Tower, and you see that it's a giant beam. That's it. It's one element. It's a giant beam. If you think of it as thousands and thousands of beams and columns, you can't design it. It's too complicated. So think of it as a giant beam. And let's go back to the first modern structural theorist, Galileo. In his article here in 1638, he didn't quite get the neutral axis right, but he got a lot of it right. And so a cantilever, so what does a cantilever have? It has to take the shear, it has to take the moments. And so we, in this book what we did that Anita helped out on, so here are different topologies. These all have exactly the same amount of column steel, but you can have a huge range of moment inertias by using the same amount of material. And so we use this concept on the Burj Khalifa. It's a concrete building as you go up. And if you look at it, it's a giant extrusion. It's like a window mullion extrusion, if you will. So, it extrudes up. We have this center hexagonal core that resists the torque, so it doesn't twist. And then going out the lanes, we have these walls down the corridor that act like webs. And then we have these cross walls that act like flanges. So that's how the system works. And this is the structural system for the Burj Khalifa, okay? So basically, the guy's front leg is the core, his back leg is the buttress, and we call it a buttress core as it resists the wind loads. The other thing, of course, we did was we managed gravity. We pushed the loads outward. And so when you get to the bottom, if you walked up to this job site and someone asked you how tall the building is, you probably wouldn't say it's over 160 stories. Okay, we had zero tension even in a storm that happens once every 1,700 years. A little bit of the geometry of scale. This is also by Galileo, and guess what? He drew it correctly. I always thought this is an exaggeration, but no. If you do the calculations, if you have something that's cantilever and it's about to break under its own weight, and you make it 3 times longer, well, you got to make it wider, but as you make it wider, it gets heavier. And so this is actually the way it scales. And this applies to animals, but it also applies to buildings. If I were twice as tall, I'd be twice as wide, twice as thick, and I would weigh 8 times as much, okay? I don't scale very well, all right? And so whenever you go from one scale of building to another, which is a very point of geometry, you have to hopefully either evolve or maybe better yet, invent a new species. You could say these are structural systems. I call them structural species, where each is an animal that exists at its own scale. So here's a photograph that's very familiar to somebody in the audience here. So here we have a bunch of tall buildings at a cocktail party, each expressing their bones and their structure that hopefully still expresses the architecture. We were asked what matters today. You guys. This is what matters, okay? We as structural engineers are going to have a big impact on the embodied carbon going forward. And if we don't do it right, no one else is going to do it. So, that is a point I want to make. I want to invite you all to Madrid in a little less than a month. The SOM Foundation is going to have a symposium on creating new architecture through research, here in Madrid. And if you go to the SOM Foundation website, you can get more detail. With that, thank you.
Bill, thank you so much, and sorry that I hustled you a bit. Please, some questions, some insights? Dearest one.
Yeah, thank you very much. The cross bracing we see on the picture here has a plate between both ends, but the technical drawing you showed a sliding mechanism like a bolted lock or something. Is it correct that the sliding mechanism was no longer necessary because it breathes out and in?
Our first concept, the one we did in Australia, has a mechanism where it actually slides horizontally but does not slide vertically. Here, no, this is just a plate. There are no joints, everything's there. And what happens, the plate and the plates, they just flex. You cannot fight thermal loads. You can, the bigger you make it, the worse it gets. So we wanted to make those plates as thin as we could so that it could uptake the curvature that was needed, but at very low stress. And so, yeah, and then we did, this isn't my favorite bolt splice because you have bolts in tension, but I prefer the lap splices. But anyway, so we bolted in there, And then, this piece in the middle is just it's high strength steel, but very thin. Yeah. Hope that answered your question.
Where do you find your inspiration for geometry forms from?
Oh,
Yes, how do you get inspired, you know?
they,
And do you think there are limits?
Where do you find your inspiration for geometry, and is there a limit?
my inspiration, I don't know, just curious, I guess. And I work with a lot of very curious people, and so we're really studying geometry. And the more I look at geometry, the more I'm convinced that's what we need to really understand is geometry. And we try to publish everything we find. We try to publish it. Okay. So hopefully it's out there, in that you can find it. If you can't find it, send me an email. Yeah, about our stuff. Yeah.
Yeah, thanks a lot of these things. You started by Maxwell and Mitchell
Yeah.
in planar systems, and you ended with 3D systems. Now, what helps Maxwell and Mitchell in spatial systems?
Well, you have to throw in Calodyne and some other people to get it to work in spatial. It turns out that the load path theorem applies in 3 dimensions. It's not just a 2-dimensional. Maxwell's load path theorem, that's the basis of Mitchell. And Mitchell did do a torsional ball in his 1904 paper. But trying to find the minimal 3-dimensional Mitchell truss is not easy, okay? We had an intern one time, and ended up getting a master's at MIT. I think they should have given him a PhD. He did some kind of tensor, torsional shell. He was able to replicate it. But in 3 dimensions, it gets more complicated. Unfortunately, a lot of the 3-dimensional structures we do we call them 2.5 dimension. Like if you have a roof, it's a 3-dimensional surface. It's a 2-dimensional surface in 3 space, okay, like a roof. And so, and one of the things we like to do is we like to take a 3-dimensional problem and make it a 2-dimensional problem, and then pop it back to 3 dimensions. This highly derivative of the stuff that Philippe did, back in the day. And so, if you have a structure like a roof structure that's in equilibrium under gravity, then if you look straight down, and you see a 2-dimensional object, but you no longer see gravity. If you look parallel to gravity, you no longer see gravity, but you still have to develop the thrusts and the forces. And so we find that it's interesting to look at, how many thrusts can you make, and what's the nature of the thrust that you can do. So a lot of times our 3-dimensional solutions are related to 2-dimensionals, and then we use force density to pop to the 3rd. Now, another ETH graduate, Masood from University of Pennsylvania, is doing some stuff in 3-dimensional graphic statics, where you take a 3-dimensional object and and it's I won't even start to explain how this works, but it's another rich field for going to equilibrium. And all this is about equilibrium. And okay, I got to do a plug here. Yeah, give me my briefcase. Yeah. I got a book in here. All right. Where is it? Okay. Some of us in the room here have been spending the last 10 years writing this book. It's on the geometry of equilibrium, where we've taken the work of James Clerk Maxwell and tried to understand what he was doing. And a lot of the stuff he did was absolutely brilliant, but ahead of his time, and a lot of it got forgotten. And because they didn't have the computer graphics, they didn't have the tools we have today. And so, it took us 10 years. Well, where's John? Okay, John, Philippe, and probably some other people in the room, we met in 2015, says, we got to write a book. And so it took us 10 years to do it, and we finally got it out this year, okay? So geometry equilibrium, a little plug there. I don't get any royalties, so don't worry.
Great. It's always great to have these books for us to bring it further. One last question.
One question to you and to Maxwell. What do you think about diagonals?
Oh. Yeah, what did Maxwell think about diagonals? If your name is Shear, they're helpful, okay? What I always talk about is when I compare the moment diagram that has no diagonals, or one diagonal, if you will, to the Pratt truss or to the Warren truss, I always tell the students, you're at the pub and you need to go home, okay? And if you can make that short, because your name is Shear, okay? And your name is Shear and you have to get home, so you got to minimize your shear path. And that's a lot of what this optimization is about, is making the shear load path more efficient. So real quickly. So imagine your name is Shear and you're going from, here's the pub, here's your apartment. How do you get there the most efficient way, And if you go to like this one, you're trying to get home, oh man, I'm going the wrong direction. Trying to get home, oh man, I'm going the wrong direction. Finally made it, okay? So, so I do like diagonals, okay?